Welcome Year 12s. I'm continuing on with the series of lessons about entropy, enthalpy, and now we're introducing a new concept which is called Gibbs free energy and feasibility. Now, you need to be aware or continue to understand what is meant by enthalpy and entropy, because these two ideas are very, very important. Remember, the enthalpy is the amount of disorganisation or chaos within the system. Now, we essentially want this to be a positive value. Okay, if it's a positive value, then the disorganisation is increasing and therefore it's more likely to occur. With enthalpy, which is delta H, we want this value to be negative because it's exothermic, so it's giving heat out to the surroundings, so the reactants have more energy than the products, so the excess energy is given out to the product. If we have both of these added together, then essentially you can see that from this equation that delta H minus T delta S, T being the temperature, if this overall is negative, the overall reaction will be feasible. So essentially what we are looking for is for this reaction to, for this equation to come up with a negative value and therefore show that the reaction itself is feasible. Now, few things, you can read through the notes on this and it's very, very clear on this. It says a decrease in enthalpy is more favourable in the chemical reaction, an increase in entropy is more favourable in the reaction. Overall, we want the value to be 0 or less for the reaction to be feasible. There's a little bit of a caveat added here which explains about the misuse of the word spontaneous, because generally the word spontaneous means that we think of, oh, it happens instantly in reaction straight away. However, that's not necessarily the case. For example, rainwater on a bike is a spontaneous reaction. However, the rusting that occurs takes weeks to happen because it's a very, very slow chemical reaction. The spontaneity of a reaction or the feasibility of a reaction does not mean that the rate of reaction is quick. Now, this table here is looking at ideas of whether the reaction is feasible or not feasible at different temperatures. It takes a little bit of a while to go back to work through this. So I would suggest that what you actually do is write down this equation and think about how this table affects it. So for example, if we've got delta G is equal to delta H minus T delta S, what we've got is, if we look at the top value in this, and I can do this as an example, if delta H is negative and delta S is positive, no matter what value I put into these numbers, if that's negative and that's positive, the overall result is going to be a negative answer. Okay, because this number itself is negative, we've got minus T, so even if you've got, say, 1 degree Kelvin in there, then delta S, if it's positive, will also be this would make this all subtractive, so this number is going to become more negative. So that's why it says delta G is always negative, feasible at all temperatures. If this statement here that we're looking at, if we've got, say, delta G and this number is negative, then the caveat with this, as long as t times minus s, you can see those two numbers times together will be a positive value, is smaller than the delta H. So I do apologise, I'm getting side column there. Then is smaller than delta H, then that equation is feasible. So it will only work at low temperatures. If minus T delta S makes this bracket larger than this, it becomes unfeasible or not feasible because the reaction makes the delta G positive. I'm hoping that will give you a bit of an idea. It's actually worth just sticking random numbers in and start to see how that works. Okay, so that's the first idea of this. So Gibbs free energy, obviously named after a scientist called Gibbs, has come up with this idea that he says, right, if I get this Gibbs free energy and it's a negative value, then the reaction is feasible. It can possibly happen. Doesn't necessarily mean it would happen, but it can possibly happen. Well, on the next page, we then start to put a little bit of this application in place. Okay, so it says here, step 1, calculate the delta H, delta S and delta G for the reaction at 298 degrees Kelvin. Okay, so I'm underlining the details there. And it says, is the reaction feasible at 298 Kelvin? So, what I've done, without any further details on this, I've actually just sat down and thought, right, if you're going to work out delta H, we know that delta H is the sum of the delta H formation of the products minus the sum of the delta H formation of the reactants. So looking at this equation, this is the reactants, these two are the products. Okay, so if I'm going to work this out, I'm looking at the table, we've got the delta H formation here, and notice they're in kilojoules per mole. So if we're going to work this out, we've got products minus reactants. So I'm going to put these into square brackets, just so I'm grouping them together. So I've got minus 348 minus 394. And then I'm subtracting from that the reactants, which is minus 812. And that's our sum. So plug that into the calculator, keeping your brackets in there, and we get our answer as being positive 70, and I'm really trying to make this as obvious as possible, kilojoules per mole. So including, oh gosh, that's focus, isn't that? It's bad. Come on, focus. Better? There you go. So let's go do some more. If you notice, I've tried to, wherever possible, do that a little lowercase k, because the little lowercase k means kilo, or 1,000 joules. So that's 70,000 joules per mole. That will become relevant in the next section. Right, this one. Same equation. Delta S is the sum of the entropies of the products minus the sum of the entropy of the reactants. Okay, so products, we've got square brackets 44 plus 214, and we're subtracting from that 83.0. So I should put the decimal points in here because we're keeping the consistency of the number of significant figures. So we've got that value, we stick the values in, and in this case we end up with positive 175 joules per mole per Kelvin. Now this is a capital K. So this is Kelvin, as in the absolute temperature scale. Make sure that you'll see why in a second I put this at the end, because it gets confusing otherwise. I've written this step conversion Notice, this is in joules per mole per Kelvin, this is in kilojoules per mole. So what I'm going to have to do is convert 175 joules per mole per Kelvin into 0.175, which is divided by 1000 kilojoules per mole per Kelvin. Okay, you can start to see there the difference between the K's. This is why it gets a little bit confusing in this one. Right, once we've done this, and we've got this value here, what we can actually then do is substitute this in. I'm going back to the question, what is the temperature? Temperature's in Kelvin, so it's 298 Kelvin. So delta G is equal to delta H, oops, that's not right, the delta H. Delta H was this value here, which is 70, minus the temperature, which is 298, and I'm going to put it in brackets just because it's easier to access this like that. So that will be your calculation, so you put it into your calculator. And what you've got to get then from that answer is, you notice all the numbers of three significant figures. So when we're writing this down, it's 17.9 kilojoules per mole. Okay, so just checking that, is that right? I'll let you have a think about that, because what would the units for delta G be? Because at no point it's seen yet, but I'm looking at this. I'm thinking I'm missing a K somewhere. That's your first task, work out what the temperature is and what the value for that would be. Okay, now, it's a positive value. Question 2 says, is it feasible? Delta G is positive. I'm going to write the word therefore. I'm also going to put in brackets 3 dots, which is the replacement of it. Therefore, it's non-feasible. Right, last question says, give the temperature range in which the decomposition of zinc carbonate is feasible. Now, this is the bit where you have to have a bit of mathematical logic to your thinking. Right, for it to be feasible, it has to have a delta G of 0 or lower. Now, if you keep that in mind, that then actually makes this quite easy to work out. It's quite easy to work out because if its delta G is 0, then using the equation that we've been using to here, then if I go delta G equals 0, delta G equals 0, then delta H minus T delta for it to be feasible. So I can actually then rearrange that formula to delta H equals T delta S. You can then rearrange it to work out the temperature which would be feasible. So T is equal to delta H divided by delta S. Silly icons get in the way again. Okay, so if I put the values into that, here's our delta S, here is our delta H. So for it to be feasible, it has to be with a value of these two cancel out, which is 400 degrees Kelvin. So any temperature that is greater than or equal to 400 degrees Kelvin would mean that that reaction would automatically decompose. Okay, because in order to do that, it needs to have this delta G being 0 or lower. So the moment it hits 0 or lower, it will start to decompose. Okay, that's our first example. This is very, very standard in how we work these things out, and you'll see lots of questions like this. This one, you need to get your head around. Okay, to me, graph looks wrong, upside down, backwards, but that's where it's actually thinking. Okay, we are talking here about changes of state, so evaporation, condensation, and so on and so on. So if we think of it that way, for a reaction to change state from a solid to a liquid, then the temperature must be high enough so that it overcomes the bonds and overcomes the enthalpy of vaporization, or the enthalpy of liquidation, if that's a word. I think it's really correct. So what we're saying that is at those points, delta G must be equal to or less than 0. Okay, so if we look at this point, if we have a temperature that is lower than its melting point or boiling point, delta G is positive, and therefore it's not feasible. As the temperature rises up, we get to a point where delta G is equal to H minus T delta S. That will then hit 0. So at this point, the amount of disorganization is higher than the entropy. Well, disorganization is which is minus delta S, contributes a bigger value than the entropy. And I'm still using the wrong word, so I'm getting distracted. So going back to the tables, you can check on this from the previous tables. So going back to it's at this point, okay? So we've got temperatures lower than delta G, it's positive. At temperatures higher, then it's negative. So we are working on to go from we've got positive delta G, positive delta H, delta S is becoming more positive as its disorganization increases. So therefore what we need to do is have a higher temperature to overcome or make this value more negative, so that it actually then is what is feasible. So that's where this comes in. So up until here, because we have to put energy in to make it melt, we've got a positive delta H because it's endothermic, melting is endothermic. Because we are changing from a solid, which is very organized, very structured, very little movement, the delta S for that is very low. As it turns into a liquid, the delta S will increase. So if we've got both of these positive, if we're using delta G is equal to delta H minus T delta S, if this is a positive value, we need quite a high temperature for it to overcome this positive value. So that's what it's saying is a set temperature at which it turns from a liquid to a gas, and then after that the T part of it counteracts the delta H, so therefore it's feasible that it was spontaneously, so feasible that it would turn into a liquid. At this point, boiling point, same idea, same concept. So the questions down here actually turns around and says the enthalpy change for melting of potassium chloride is positive 25.5 kilojoules per mole, and the entropy for change is 0.245 joules per mole per Kelvin. Notice the difference in values. So the first one, I'm going to write down the equation, delta G or delta H minus T delta S. Delta G has got to be 0, because otherwise it's not feasible. Delta H is equal to 25.5 kilojoules per mole. Delta S is equal to 24.5 joules per mole per Kelvin. I'm now going to convert that to kilojoules per mole per Kelvin, and T is the thing that we need to work out. Okay, now from the previous calculation we worked out that T is equal to delta H divided by delta S, so we've got 25.5 divided by 0.0245. So the temperature for this would only be feasible if it was over 1040 degrees Kelvin. Is that okay so far? Do you understand that? So all I'm doing is, you can see that I'm structuring this exactly the same. I've got my equation, I've written down these and then did the conversions here, and then I've done the values down the side. Okay, it says here calculate the entropy of vaporization. The boiling point for ethanol is 78 degrees. Calculate the entropy change for vaporization. So delta G equals delta H minus T delta S. Equation delta G is equal to 0 because it won't be feasible if it's a value greater than 0. Delta S is our question mark, that's all we're working out. T is 78 degrees C, which is equal to 351 Kelvin. There we go. And that leaves us with delta H. Which is 43.5 kilojoules per mole. Okay. Rearrange this equation and we end up with delta S is equal to delta H over T. Remember that was 0, so we can end up with 0 is equal to delta H minus T delta S. So we can move this over, so T delta S is equal to delta H, then we want the delta S to remove the T down underneath and end up that equation. So now we are substituting in our values, so 43.5 divided by 351, and very quick calculator on this one. Oops, I haven't got the calculator, what have I done with it? Bear with me a second, come back to my phone. And about to be invaded, I think. My son daughter's just woken up. Do apologise. 43.5, oops. Divided by 3.5 equals. Right, delta S is equal to 0.123. Okay, now I'm hoping you can see how we work these things out. Oh, sorry, too rough to deal with. I hope you can see how I can work these out. If you have any problems, please feel free to email me.